Okay, so you've hopefully plotted the data, got a graph, and what we have is something that will probably look a little bit like so that, and then that, sort of a weird sort of shark thing. But we'll come to that in a moment, and that occurs because if we keep stretching a spring, eventually we pass a point called the elastic limit, and once you go beyond that, your spring is permanently deformed. It won't go back to its original shape, which is hopefully stuff that is memorable from GCSE and from doing that. So what we have is this sort of like so up until the elastic limit, spring will stretch according to Hooke's law. So that is saying that we can apply F equals K X. Now that it's called the elastic limit because in this region the deformation is elastic, which means that the spring will return to its original shape. So in this region, the deformation is elastic. So that means it will return to its original shape once the tension is removed. Okay. However, beyond the elastic limit, we enter a region we call plastic deformation. So beyond the the deformation is plastic. Apologies for the extra things there. I'm going to undo that and get them go away. Yeah, there we go. Oop. Drop my pen. Beyond the deformation is plastic. Okay, so that is permanently deformed. So examples of plastic material, something like blue tack or chewing gum. You stretch it, it won't go back to its original shape. So what we end up with when we plot our loading and unloading curves, though, is we end up with something like this. Okay, so this is the data I collected. It's in Excel. So if you hadn't gone past the elastic limit, then a loading unloading curve would essentially be on the same line. You would load up that line, and then unload would come back down the same sort of line. So then blue. So they would just basically go back exactly the same as it is. But we're not. So let's delete that. We don't want it anymore. This is a loading unloading curve for the spring in question. And we can see that there are kind of three sort of regions to be aware of. And I've tried doing this with the ruler. It's really fiddly, so I'm not going to do that. I'm going to just try and draw my straight lines. That's a lasso topic. So in a loading unloading curve, identify sort of three sort of regions where we're kind of interested in what's going on. So the first region I'm going to do this in blue, and this is going to be a bit fiddly to try and get it all to the right place. My best effort at drawing a sort of straight line. Terrible straight line. But we have sort of this region, which is, we have a loading region where we're following Hooke's law, and we've got elastic deformation. Eventually, however, we go to a point where we, let's go green, we sort of pass the elastic limit, and we end up with a sort of a curve that's going to go like that. Okay, so we've got, this is where we've got plastic deformation. But then we have our unloading curve, and the nice thing about that is it's actually reasonably a straight line. So we end up with, so it looks like, of that. Now, there's something, we can see that as being, so we've got loading following Hooke's law. We've got in green, we've got loading with plastic deformation. And then in red, we've got a sort of unloading. And it's a kind of a linear, sort of a linear region once again. So it's actually still behaving much like a spring. In many ways. It's just not going back to its original shape. And if you think about what it looked like at the very end, it still was essentially a spring. It's made a sort of a new length of spring, one that actually, you could compress and stretch. It still had a sort of springy quality to it. We hadn't completely destroyed the nature of being a spring, but it was no longer the same nature of the original spring, which is so we would still not, we wouldn't use the term of saying it's still following Hooke's law, because we know what we started with. So we don't use that term again, even though it is sort of roughly sort of linear. Now, there's something important to recognize about this, okay, is there is an area in this curve that's bounded by the two lines. It's sort of this area here. So this area between the two is something that's kind of important, and this would be helpful. Oh, wow, Mr. Tickney, you can nearly color inside the lines, but you can't quite. So if we think about the fact that the area under a force extension curve or line is the work done, well, what does that represent? That is a difference in area. That is a difference in area, and hence a difference in work done. Now, the line, the area under the blue and the green line, the loading curve, that is the work that we've done in stretching the spring. So that's the work done stretching the spring. The area under the unloading curve is the opposite of that. That's the work done by the spring on going back to its original shape, and that will be released via sort of thermal energy or maybe kinetic energy if you make the spring bob up and down and stuff. That green area, that difference, that is the work done that's been absorbed by the spring in permanently deforming, and hence is now stored with, it's just part of the spring now. It's not, that's the work, that's the energy that's basically been absorbed by the spring in order to permanently deform. So we can actually calculate the amount of work that's been done in permanently deforming the spring, because you put in the stuff under the blue and green lines, you can get back out the stuff under the red line, that's coming back out. The stuff in the green area, well, that's staying inside, that's stayed and been absorbed by the spring. So gonna move that just down there. So as the represents the work done. On or by not quite work there. I don't want to use the word work. Represents the difference in area represents the energy absorbed by the spring in permanently deforming. So that's sort of the energy that's sort of now inside. That's internal energy sort within the spring in sort of taking onto a new shape. So we can calculate that, and that's what you're going to do with your graph, is to go back and to estimate the area under each line and get a value for what that green area represents. Okay, so how big is that sort of area between your two curves? Now, just to sort of make it a bit clear as to what you want that to be. Okay, I'm going to zoom out a little bit here. Here's how I sort of would divide this up. Is I would recommend, wrong one, that the blue area sort of you have a nice sort of that kind of nice and easy. You've got sort of a triangle that you can work with there. Hopefully you have a ruler, but you've got an area under that. That's easy. That's a triangle, so you can do a half times base times height. That's easy enough. For the red one, you've got to make a call as to how far you fill the loading area. You can work out how much you get in terms of for how far you can go up as a straight line before it starts pulling away. So maybe up to about there. And rather than making it overly complicated and saying, oh no, I've got to do lots of triangles, I would just kind of do an estimate. So you then got a rectangle, and then finally you can have a sort of another triangle there. So you can have a triangle there, and a rectangle. So you can sort of add up, say, maybe 3 areas and get an idea of, of what these sort of various things are. Of course, with your one, I really hope you're able to use rulers and draw straight lines, unlike me. But try and work out how much energy was ultimately absorbed by the spring in permanently deforming. When I did the calculation earlier, I did get less than a joule, but that's to check. So there we go. That's how we can use this kind of stuff. Smiley face.